In modern cardiovascular, nephrology, and oncology trials, evaluating long-term outcomes is a complex mathematical challenge. For decades, the statistical standard has been the time to first event, or TTFE, composite endpoint framework. A standard TTFE analysis takes multiple adverse clinical outcomes, like all-cause mortality, a non-fatal stroke, and heart failure hospitalizations. Patient B is in the control arm. They experience 0 hospitalizations, but they suffer a sudden cardiac death on day 31. Patient A is in the active treatment arm. They receive a highly efficacious drug that saves their life. Because they survive the duration of the trial, they live long enough to experience 3 minor hospitalizations over several years. Under a TTFE analysis, patient A's analytical timeline is permanently truncated at their very first minor hospitalization. All subsequent data, including their long-term survival, is completely discarded by the model. This creates a severe statistical paradox. The model declares patient B's outcome as equivalent, or mathematically better, simply because their single fatal event occurred 1 day later than patient A's early minor hospitalization. The statistical machinery behind this, typically the Cox proportional hazards model, treats all events equally. A non-fatal, easily managed, transient hospitalization is given the exact same statistical weight as a fatal cardiac arrest. To see how this distorts clinical reality, consider 2 hypothetical trial participants. To address this, statisticians introduced the win ratio methodology. Instead of evaluating aggregate hazard rates, the win ratio structures outcomes into a strict, predefined hierarchy, placing irreversible events like mortality at the absolute apex. The win ratio provides a mathematical structure to enforce this clinical priority, ensuring that survival data remains a visible part of the primary analysis, even when lesser morbidities occur early in the trial. Executing the win ratio requires forming patient pairs. Early iterations attempted a matched pair approach, linking individuals based on strict baseline risk scores. Because finding perfect clinical matches is difficult and discards data, modern trials overwhelmingly utilize the unmatched approach. In the unmatched approach, every single patient randomized to the active treatment arm is systematically compared with every single patient in the control arm. This universe of pairs is generated using a Cartesian product equation, where the number of treatment patients is multiplied by the number of control patients. In a trial with 1,000 patients in each arm, the algorithm evaluates exactly 1 million mutually exclusive patient pairs. Once a unique pair is formed within this massive matrix, their respective clinical trajectories over the duration of the trial are pitted against one another using that strict, multi-tiered hierarchy. This flowchart shows the formal algorithmic evaluation structure. The comparison begins strictly at the apex of clinical severity. For every pair, the algorithm first queries Tier 1, cardiovascular death. If one patient experiences a fatal event earlier than the other, a definitive win or loss is recorded. At that exact moment, the pairwise comparison terminates permanently. No lower-tier data is considered. Only when a pair cannot be decisively resolved on mortality, either because both survived or both died at an indistinguishable time, does the algorithm record a tie at Tier 1. That tie acts as a trigger, cascading the evaluation down to Tier 2 to break the deadlock using morbidity events like heart failure hospitalizations. If the patients tie on hospitalizations as well, the algorithm cascades down again to Tier 3, relying on quantitative biomarkers or functional tests to find a clear winner. By mathematically locking in fatal events at the highest tier, this top-down cascade aligns statistical weight with patient-centered priorities. Survival benefits are secured before lesser morbidities can influence the comparison. After traversing the matrix, the millions of paired outcomes are aggregated. The primary win ratio test statistic is calculated as a simple relative quotient, total treatment wins divided by total control losses. This metric incorporates the entire universe of pairs, including ties, into its denominator, generating an absolute measure of effect size strictly bounded between -1 and +1. Similarly, the win odds metric stabilizes the math by symmetrically distributing the tied pairs into both the numerator and the denominator, preventing division by zero errors in datasets with massive volumes of ties. Establishing these metrics used to be a computational challenge. Estimating the variance of a massive Cartesian matrix originally required up to 30,000 non-parametric bootstrap resampling iterations, placing a significant burden on computing resources. A major methodological breakthrough arrived when biostatisticians successfully derived closed-form variance estimators. They achieved this by utilizing the logarithmic asymptotic distribution of U-statistics. This U-statistic framework mathematically links the variance of the sample directly to the overall proportion of tied pairs expected within the trial. As the proportion of ties increases, the variance expands. Utilizing this closed-form variance equation removes the bootstrap computing bottleneck, allowing trial sponsors to run precise, prospective sample size calculations during the design phase of a Phase 3 study. Despite its mathematical elegance, the unadjusted win ratio encounters a methodological vulnerability when deployed against the messy reality of longitudinal clinical trials: administrative right censoring. This introduces a floating timeframe structural bias. When the algorithm compares two unique individuals, the effective evaluation window is strictly limited to their minimum shared follow-up time. If patient A is followed for 5 years, but patient B drops out and is censored at year 1, all data collected from patient A during years 2 through 5 is algorithmically discarded for that specific pairwise comparison. Within an artificially truncated 1-year window, the statistical probability of a top-tier mortality event shrinks drastically. This effectively forces an artificial tie at the apex of the hierarchy. The final test statistic is no longer a pure measure of therapeutic efficacy. It becomes influenced by the trial's random dropout rate. To satisfy strict international regulatory guidelines, methodologists must formally define an estimand, a precise target of estimation, to untangle the true underlying treatment effect from this variable censoring noise. The dominant non-parametric approach achieves this by artificially pre-specifying a fixed, uniform maximum censoring time across all pairwise comparisons, known as a tau restriction. This completely stabilizes the comparison window. However, truncating the data artificially induces its own missingness. To correct this, statisticians apply inverse probability of censoring weighting, or IPCW. This mechanism mathematically upweights the specific patient pairs who successfully remain uncensored for the full tau duration, creating an unbiased pseudopopulation. Without the rigorous application of a predefined estimand and IPCW adjustments, an unadjusted win ratio can become a structurally biased artifact of the trial's administrative timeline. Managing millions of Cartesian calculations and complex IPCW weights requires validated computational infrastructure. Biostatisticians rely on specific SAS macros and open-source environments to execute these massive matrices. In the R statistical computing environment, packages like BiSATest and WR are heavily engineered specifically to handle these advanced regulatory designs and right censoring corrections. These software packages easily facilitate advanced extensions, like the last event-assisted win ratio. This variant solves a limitation where the standard algorithm only evaluates the time to the first non-fatal event on lower tiers, leaving subsequent morbidities uncounted. Instead, the last event-assisted framework evaluates the cumulative frequency of recurrent hospitalizations over the patient's entire timeline. It mathematically rewards therapies that delay the overall accumulation of disease burden over time. But regardless of the software used, trial steering committees must navigate a statistical vulnerability: the profound mathematical sensitivity to subjective endpoint ordering. A Phase 3 trial evaluating a therapy for Pompe disease illustrates this. The trial balanced two co-primary functional domains: the 6-minute walk test for physical endurance and forced vital capacity for respiratory function. When the walk test was prioritized at the top of the hierarchy, the therapy generated a win ratio of 2.37. But simply inverting the priority, placing respiratory function at the top, significantly shifted the total pairwise wins, contracting the win ratio down to 2.02. Because the math is sensitive to evaluation order, the exact sequential hierarchy must be rigidly pre-specified in the statistical analysis plan prior to data unblinding. This prevents post-hoc data dredging and preserves the integrity of the analysis. As this methodology becomes an industry standard, clinical reviewers must avoid a prevalent misconception: the assumption that a win ratio behaves mathematically like a traditional hazard ratio. The hazard ratio relies on a maximum partial likelihood framework to measure instantaneous relative risk. It assumes continuous proportional hazards across the entire observation period. The win ratio is different. It is a generalized non-parametric odds metric. It represents the holistic probability of achieving a multidimensional better outcome within a combinatorial pairwise matrix. Interpreting a calculated win ratio of 1.30 as a 30% reduction in instantaneous risk is a statistical error that misrepresents the data. It quantifies the odds of winning, not the precise magnitude of the underlying hazard. Reviewers must also watch for the soft endpoint dilution effect. Because the hierarchy incorporates qualitative assessments at the bottom, a highly significant headline win ratio might be driven entirely by subclinical improvements in a survey, even if the mortality results are neutral. Furthermore, unmatched pairing mixes different baseline risk profiles, adding statistical noise. To manage this, biostatisticians must deploy advanced stratification, calculating baseline covariate adjusted win statistics to ensure the final effect metric is accurate. The final operational requirement for regulatory statisticians is context. The highly relative win ratio must always be complemented with absolute measures, like the net benefit, to ground the abstract pairwise math in clinical reality. With rigid pre-specification and transparent censoring adjustments, the win ratio measures therapeutic impact across a prioritized clinical hierarchy, reflecting the multifaceted nature of chronic disease outcomes.